Okay, hi Chris.
Okay, so full disclosure, we are currently recording. So, plan for not hiding, not recording you secretly. You are actually being recorded. I'm telling you so.
Wow. Are you? What if you do?
Yeah. So.
He recorded.
Yeah.
My Spanish teacher in like 4th grade, she recorded our class because she thought we were all bad kids, and then she got fired.
So that's why I'm telling you that you are being recorded. I'm not doing it secretly. I'm doing it for the purpose of learning stuff. All right. So plan for today. First, if we have questions relating to the lab that you would like answered, we can do that. Then I will entertain any questions you have regarding studying for your test scheduled for tomorrow. Then we'll go from there. Okay. So first, any questions relating to the lab over the weekend? Laura, go ahead.
Okay, so I have 2 questions for the lab.
Okay.
So first, zero like kind of brought the whole thing down, because like I thought it kind of confused.
It shouldn't have. I'll show you why in just a second. So if it's different size, that it's gonna like pop up here. So I wrote you an email back this morning. But it shouldn't, depending on the numbers of the path. So here, let's go here and pull the data up. All right, make this bigger here, and let's grab this. Okay. All right. So there's our data for the car, but it says to calculate the average velocity for each interval. First thing it's asking you for is this and this, right? This is going to be your displacement. This is going to be your time because they both start at 0. For the second interval, we want to look at the distance and the time just of that interval. So you're going to have to take the difference between these two, the difference between the 2 position values, and then the difference between the 2 time values, and divide them. Does that make sense? Yes. So that was kind of confusing, I know, but I believe we talked about that on Friday. So, but yeah, do it for the intervals. That makes it a lot easier to do. So if you need to fix it. So Laura, do it, for this interval, then that interval, then for this interval, and then for this interval here, and just do it between each of the marks that we measured.
So how would attributing you take 0 and then just like 5 and 6 values?
You're taking no. If you're taking the average velocity for each interval, okay? So average velocity is equal to displacement over time, right? The displacement is the difference between where it started and where it finished in that interval, right? So for the green interval, right, here, its final position is 1.043 meters, right? Minus its initial position, which was the starting point, okay? Then the time that it takes is just 2.31 seconds because it started at 0 seconds. Does that make sense? Then for the blue interval, this is still how we define average velocity. But now, of course, that gets rid of my numbers. I don't want that. So here, we go, for the blue interval, this is the final position. So you go 2.884 minus the initial position, because we just want to know the displacement during that interval. Its initial position there was 1.043. So that's going to be your displacement. Where does it end versus where does it start during that interval?
So if your entire trip, it should have just been 9.887 minus 0.
That would be for the entire trip.
So,
For the entire trip, yes. You would go 9.887 minus 0 for the displacement, and then 21.19 minus 0 for the time. Okay? But then for each individual section here, let me finish this off just so it doesn't look funny, then you'd go 6.26 minus 2.31, like that for the time. Does that make sense? Those two values there.
But you shouldn't be subtracting 0 in the third.
You can subtract 0. That's technically, yeah. Technically, Lauren, you'd go like that, but that's going to get you the same number anyway. So, does that make sense? Go ahead. Yep. Okay. So we talked about the idea that, Lauren, this is a position versus time graph, right? So if we grab this graph, if we look at the slope, first, we talked about the idea, how do we define slope? Rise over run, right? So rise over run. With that being the case, if we look at the rise axis on this graph in particular, what's on the rise axis? Position, which is measured in what unit? Meters. So if we apply this rise over run general form for slope to this graph specifically, we're going to have meters on the top of that fraction. Then, what's on our run axis? Time, which is measured in seconds. So what is the unit for this? If we calculated the slope of this graph, units-wise, it would come out as meters over seconds. Okay. What is that the unit of? Well, what is that the unit of? Velocity. So the slope of this graph telling you the velocity. What do you see about the slope of the blue line? Constant, because it's a straight line, right? The car, what did you see about the car's motion? It had a constant velocity. Then, Lauren, on the red graph, right, it starts off real shallow, right? Like there's the slope of that graph at the very beginning. But then later on, it becomes steeper like that. So that slope is increasing because what happened to the velocity of the ball? It increased, it got faster. So the slope tells you velocity on a position time graph. All right, good there? Yeah, go ahead.
So the slope is suggesting the velocity.
The slope is telling you the velocity of that object at that point for the graph. Go ahead.
Okay, on the marble,
Yep.
number 4, when you're comparing the time intervals,
Yes.
like I understand that they're increasing, but
Yes.
How should they compare?
Okay.
Is there something more to that just it should be going up because it's
Now, Alex, you asked this question before. I know you were taking attention. But number 4 on the marble, right? Okay. Dylan, did you calculate the average velocity for the whole trip? Did you get like 1.0 something, 1.04 something? Okay. And then, what did you see about the first few average velocities that you calculated for the first few intervals? They're lower than that, and then for the last few, they're what? Does that make sense from an average standpoint? If you calculated in number 2, if you calculated the average velocity for the entire trip, and then in number 3, you calculated average velocities for certain sections of that trip, shouldn't some of them be lower than the average, and some of them be higher than the average?
So that was kind of more like how should they compare also to the entire trip?
Right. Yes. How should they compare to the entire trip? Yes. Or the fact that how should they compare it? They're getting faster because if you're calculating the velocity during individual sections, we should be seeing that it's getting faster. You asked.
Oh, I think.
That night. All right. Other questions relating to the lab. Lab or objective? Okay.
Thank you.
This is all objective sheet stuff.
Me and Claire were working on this together.
Okay. Allowable.
I decided.
I think we did it wrong, but I know we just did number 3, but isn't can you go to the all right.
Or GY.
Yeah,
Or G move, not bad.
the calculation.
Yeah. Like this, right?
It's like each little box, is that considered a meter? Like the first one?
No, but that's what I wanted you. It's not exactly a meter, but that's what I wanted you to calculate. So it should have said, instead of it at 1 meter intervals, it should have said at each T mark interval. Does that make sense?
Did he take message with him?
I told him where they were. I didn't actually watch to see.
Yeah, he did. He took.
There you go.
Alright.
Yeah,
So, yeah, so sorry, Greg. For the first part, right, that would be your first interval.
yeah.
Okay, and then this would be your second interval. So instead of doing it at 1 meter at a time, I wanted you to do it for like those intervals.
So if let's you get questions wrong, say so. Questions that were also wrong.
Not necessarily, because did you see that your averages got bigger as you went along?
I mean, they're not all wrong, there's like 2 there, right?
Did they get bigger though? They should be getting bigger as you go farther down the ramp.
Yeah.
Okay.
Yep.
Regardless of where you measure them, regardless of where you measure them at, they should be getting bigger as you go along the ramp. So that should be able to you should be able to answer number 4 at least properly. Did you answer number 4 that the average velocities kept getting bigger as we went down the ramp?
Yeah.
Okay, then that's the right answer. It's just a matter of the numbers, not exactly what I want you to calculate.
Like also, like it's gonna yell at you just saying.
Because of that?
I don't know what she said. She's gonna yell at you. She told me, you made this very unclear, and she's gonna yell at you tomorrow in class.
Sorry.
Just
I will admit there were some things I should have changed on plan. So
Aha.
it's a work in progress. Yes.
You're like a round system.
Okay,
Because there really weren't sig digs.
Wait.
Oh, I'm sorry, is it yes or no question? Do you include a sign on all of your velocities, like a positive?
Technically you should, yes, because they're velocity. What?
You do the reference.
Can't you put little pluses?
Okay, ready? I need number 12, number
All right.
14.
Again. Okay.
Okay.
Objective sheet question.
4.
Number 4. Okay. Number 4 is pretty easy. All right. So number 4. Allison, as far as our coordinate system or frame of reference, Sam, our definition of a coordinate system or a frame of reference is what?
Context and motion.
What do we need to do to set up a coordinate system?
You have to find the reference.
Reference point, and then what else? A directional system. Okay. Allison, why is it important that we set up a reference point and then a directional system if we're taking measurements of something? It's not necessarily so that I know where I started,
But
so other people know where I started, right? That's why it's important. Allison, I could say that at this point in time, you are 5 meters away from me. Does that really help anybody else? If I say, hey, Allison's 5 meters away from me, does that help anybody else find you? Not really, right?
you need to be 5 meters like away from the figures.
Or, well,
Oh.
first you have to know which way are you 5 meters away from me, right? If I'm on the phone with your mom, say, she's like, hey, have you seen Allison? Yeah, she's 5 meters away from me. Does that help her find you? Because what doesn't she know? She doesn't know where I am, right? So that's the whole idea of the reference point, right? Where are we making all these measurements from? And then the directional system is, okay, if I say you're 5 meters away from me, there are lots of places that are 5 meters away from me. Which way exactly are you 5 meters? That's the importance, to
Know that.
make sure everybody's on the same page. Right? All right. What else? Tim, go ahead.
Okay, I need number 12,
Okay.
a little bit of 14, 19, and 20.
Let's start with 12.
Okay.
Okay. Sam, for number 12, we did not spend a whole lot of time talking about this in class, so I actually got rid of the question on the test. Okay? It's not, but just real quickly. Okay? Average versus instantaneous. Instantaneous is what am I doing like at this particular moment in time. Okay? Sam, let's say we took your, in order to calculate your average speed, we need to know two things, right? What do we need to know?
Like the
Distance traveled and
how fast.
nope. Distance traveled and the time that it takes you to go that distance. Okay. So Sam, let's say we figured out your average velocity from your house to Crocker Park. Okay. We take the distance from your house to Crocker Park and then time it how long it took you to get to Crocker Park. Right. That would be your average speed on the way to Crocker Park.
Okay.
But does that tell you necessarily anything about how fast you were going at any particular moment of that
Because
trip?
you could have been like sprinting and then tomorrow.
Right? Or you could have been stopped at a stoplight, waiting for the cross sign, that kind of stuff, right? Instantaneous speed tells you about, okay, how fast were you going when you went past Bob Evans on Detroit Road? That would be the instantaneous speed. Does that make sense?
Mm-hmm.
Those are the difference between those
But,
two.
okay, yeah.
But, like I said, we didn't cover that really in class, so I got rid of the question on the test that related to that. All right, 12, what else?
14,
14?
but like only a little bit of it. 'Cause
Oh my goodness, 14, we went over this like 4 times.
I know, that's what I'm saying.
Actually, we may have went over number 14 14 times.
Speeding. I know, speeding.
Speeding up,
Slowing
down.
Changing direction.
Those are your 3 physical motions.
I know, but speeding up is a positive acceleration.
Yes.
Slowing down is negative acceleration. What's changing direction?
Changing directions we would refer to actually in the physics term, it is a centripetal acceleration, but you don't need to know that term. Yes. Just you need to know, in that case, right, it would just be that physical motion is considered acceleration because it is a changing velocity. Sam, why is changing directions a changing velocity? What kind of a quantity is velocity?
A vector,
Vector. So, Nick, why is changing directions a changing velocity?
Because it's a vector.
So that means that it
It's
so you-
phase, direction, and speed.
Good. And if the direction changes, the velocity changes.
yeah, 19.
Then,
Yeah, we did. I'm so confused on the graph.
okay. There will be some graph questions. Okay. Now, a couple of things. First, you did this lab. Okay. Second, your lab quest lab, the one I just gave back to you at the beginning, we were dealing with the graphs as well. Okay. So, with that being said, remember on Friday I told you that this link right here will give you the slides that related to the graphing stuff. Okay. Here's what I want to do first. One more. Nope, too far. Come on. Where is my picture? There it is. Alright. Here's a picture straight from those slides that I gave you on Friday. Actually on the back side of page 2. First thing I'm going to do is I'm going to change this from distance to say position, which is a more accurate description of what it is. Okay? Then I want you to take 1 minute and discuss with the people around you the motion of this object. Go. Alright, let's discuss. Okay? So, Kirsten. Kirsten, how does this object start? Starts at rest. Okay? Kirsten, why is that beginning yellow section or representing something at rest? And you know that because what's on the y-axis of this graph? What's on the y-axis? Position, right? And is the position changing? It is not. Okay? All right, let's go here. That section. There's 2 things that you can tell me about that section. Okay? First, which way is this object going? Forward, right? Let's go forward with that, or in the positive direction. Okay? Second, What can you tell me about how that object is moving in the positive direction?
It's moving at constant speed and not accelerating.
Good. It is moving at a constant speed and is not accelerating. Okay? I forget who we talked about. Lauren. Okay. Lauren, what did we say about the slope of this graph? What does the slope on a position time graph tell us? Velocity, right? Remember the whole meters per second thing, okay? Nick, what do we see about the slope of this graph through that section?
It's linear.
It's linear, so the slope is what?
It's rise.
What do we know about the slope of a linear line or a line? It's constant, right? Even though I didn't draw it exactly on the line, but that is moving forward, but it's moving forward at a constant velocity. Okay? Is that good? All right. Next. That section. Okay, Allison, go ahead.
I have a question. Why is
Relating
it
to the green section or the blue section? Okay, go ahead.
why is it accelerating? It's constant speed, so it's not. What does that mean if it's not?
What does that mean? You tell me.
It's not speeding up. But how do you know that?
Because what do you see about the slope during that section? How do I know it's not speeding up? Because what do you see? The slope is constant. Okay.
It's accelerating
Now,
by curve.
Here's the problem. Okay? Can I go straight from being at rest to moving with a constant velocity? Can that happen? Can I just be like at rest and all of a sudden, boom, now I'm going 10 meters per second? No, I have to speed up. So, on this graph in real life, would we see a sharp corner like that? No. It should be more like this here, and then it like curves upward. Because during this section, now the slope is changing. It might change quickly, but it should be more of a curve.
So that point is technically it's speeding up.
At this point, at this point here, that would be where the velocity changed. But Alex, in this picture, right, it's a real it's a real sharp corner. In real life, it would be more curved, like this one.
Well, if it was like 10 meters per second, like at gravity acting on it, would that point be at 5 meters per second then?
No. This remember, this is telling you where, right? It's telling you position, okay? So it's going to be getting farther away from you, but it doesn't automatically start going at the same speed. Lauren, go ahead. Yellow part is at rest because of the fact that the position doesn't change. Blue section. What's happening during the blue section? Kirsten. It's moving backwards. Kirsten, how is it moving backwards? At a constant velocity, right? What do we see about the slope of that section? It's constant. Does it get back to the point that it started? It does not reach the point that it started again. Okay? Because if it did, it would have to come all the way back down to this section, right? To where the original line is. All right, next. This section, the green section, right? Which way, Allison? Constant velocity. Forward again, constant velocity. Let me do this. Once again, not the best arrows in the world, but what do you see about those two green lines? They're parallel, which means, Kennedy, what can you tell me about how fast it was moving forward? Same speed, right? So it has the same velocity. They're not accelerating, but they're, same speed. And then, what happens at the end? Stops, right? It's at rest again. Okay? Another way that we want to look at it, or we could look at it, right? What's the slope of a horizontal line? 0, right? What's the velocity of this object during that time? 0. Are we good there? So that, Sam, I think, are we still doing yours? I can't remember.
Yeah.
That's pretty much number 19.
It's just like kind of like fine, like.
Can you, if I give you that picture, can you tell me what's going on?
Okay. 21, please.
Okay. 21. All right. 21 is the next kind of graph. Okay. Which is a little bit tougher. Okay. So let me go here. And once again, this is on those slides that I gave you on Friday. All right. Notice what's different about this graph than the previous graph. Okay, none of them are kind of constant. There's one big important difference.
They're not sharp.
Okay. This graph is telling you the velocity of that object, not the position, right? Position tells you where something is. Velocity tells you what it's doing. Starting off, there are two sections on this graph where this object is at rest. Discuss in your small groups. Where is this object at rest? Go.
Which one's the second?
What?
Meters is the active. But which one is second to meters? It's at that point in the graph. They also got there. And also, that's it.
Yeah, that's what we said.
All right. Okay. So, the first question I asked you, Kirsten, was what? When is this object what? At rest. In order for an object to be at rest, what does the velocity have to be? 0, right? Here's what's going on in that section right there. It's not turning around. It's moving with a constant, let's not go speed, let's go velocity. Because it's also its direction is not changing either. Okay? So yeah, those two on a position graph, right? Any flat part means at rest. But on a velocity graph, where does the flat part have to be? At 0 in order for it to be round. All right, on this graph, there are two sections where this object is slowing down. Discuss. Go. Where is this object slowing down?
Wait, what's this velocity have to be?
Well, from there, wait, are you sure?
All right. So, in this graph, the two blue sections show an object slowing down. What's happening in both of those blue sections to the y values? Dominic.
Wait, sorry.
Niraj, what's happening to the velocity values during those two sections? They're going towards 0. During this section, right? Niraj, which way is this object still moving in that section? No. Positive or negative? Positive. Was that just a guess, Niraj, or was that? Okay. That's fine. I just want to make sure so we know. Okay. So, Niraj, here, and Niraj, this isn't just for you, it's for everybody. Yeah. The sign on velocity tells us what? Which direction you're going, right? So, during this blue section, right, Niraj, what sign do those velocity values still have? They're still positive, so that means I'm still moving which way? Forward or backwards? Forward. But what's happening to me as I'm moving forward? Slowing down. Here, right? Niraj, what value do those velocities have in that section? Negative. So now I'm moving which way? Backward. But what's happening to me as I'm moving backwards? No. This one here, you're slowing down because those values are still negative, but they're getting closer and closer and closer to what? 0, right? Remember, the negative on the velocity doesn't tell us fast or slow. It just tells us which direction we're going, okay? Maybe, go ahead.
Is that like a, like, can you make it a analogy to that object up there?
Sure. Ready? If you're watching class recording, this isn't going to work, but okay. So, how do I start? I rest. What's the first thing I do after I start moving?
Going faster.
Going faster, right, in the forward direction, right? So I'm going faster, 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 right?
And
then
you're
the second yellow section. What am I doing? I'm going constant, still forward, right? And then I'm going to slow down, slow down, slow down, slow down, slow down.
Oh, so that's like the
Okay.
blue part?
Yeah. So, wolf. Go up there. No, here. Go up there. Press the red pen over on the left-hand side. Okay. No, way over on the left. Okay. No, hit done.
Bottom right corner.
And you're yeah.
Oh my gosh, I can see how annoying that gets.
Now, where am I on this graph? At the 200 mark. Okay? Because the whole time I've been going which direction? I've been going forward the whole time. Okay? I sped up and I slowed down, but I'm still going forward. Okay? So, whoa. Give me a little arrow right where I am right now. Right in the forward.
What happened?
It was weird.
That's fine. Okay. Now, what starts happening next? What's going to happen to me as I'm going backwards? I'm speeding up, though, as I'm going backwards, right? Faster, 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 faster. But then, right, when I get to that dip at the bottom, right, I'm still moving which way?
Forward.
I'm still moving. At this point right here, which way am I still moving?
Backward.
Backwards, but now what's going to start happening?
Faster. Slower.
Slower, 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 slower.
But you don't.
Whoa!
No, because remember, this graph tells you velocity. It doesn't tell you where, it tells you what I'm doing. Okay, does that make sense?
Yeah.
That means that during this section right here and this section right here, I'm speeding up during both of those sections because I'm moving away from zero. The graph is moving away from zero.
Wait, and what?
The green section's out. During the green sections, I'm speeding up because that graph is moving away from the x-axis, away from zero. Okay, does that make sense? We do that. What don't you get?
The fact that it's going up and still slow.
Because remember, right, Alex, during this blue section here, what's happening to the y values? No.
Oh, it's getting close to zero.
It's getting closer to zero. They're actually decreasing because remember that the negative doesn't mean small, it just means direction, right? This is a real fast velocity. This is a real fast velocity. Just what's different about them.
Oh, so the closer it gets to zero, the slower it gets.
Because the closer it gets to zero means the slower it's going, right?
So, like,
This is slow and this is slow. They're just going in different directions.
from the point where it's at rest next to 300 to the point where it starts to go faster again, it starts to slow down, that's going faster.
That's going faster the whole time because what's happening to my y values during that section? Farther from zero. They're actually getting faster. They're just getting faster in the negative direction.
So, at the yellow, the yellow highlighted area on zero.
Yes.
Get it? That's when you're stopped.
That's when you're stopped. On this graph, I'm only stopped if I'm on the x-axis. Okay? But in the previous graph, right, any flat part, I'm stopped because that's telling me position, right? Does that make sense? Because if my position stays the same, that means I'm not moving. On this graph, any flat part means I'm at rest. But on this graph, where does my flat part have to be? It has to be on 0, because it's telling me velocity. Allison, go ahead. No. This one, sorry, which one? The one before me, right? Yes, the one before.
This velocity one is telling you what you're doing.
Right.
What is that? Like you're speeding up.
Yes. Right.
So not like if you're going.
Well, it does tell me that as well, but it doesn't tell me where I am, right? Right here, Allison, the point I was trying to make with my motion. Here, this green section is going up on the y-axis. This blue section is going down on the y-axis. But because this graph is telling me my velocity, they're both positive. That means in both cases, I'm still moving which direction? Forward. Even though one's getting bigger and one's getting smaller, one looks like it's going up, one looks like it's going down, but from a velocity standpoint, I'm still moving forward because those values are always positive. Okay? All right, how's that? Those are the kind of questions that, might show up on your test as far as analyzing the graph. Yes, John?
What's the test overall look like?
It's going to look exactly like all your other tests are on. Just because it's a physics test. No, I'm being serious. It's going to be multiple choice. It's going to be some short answer questions. It's going to look exactly like your other tests, just over physics stuff. So, the format of the test is not going to change. 35, I think.
In your autograph,